Thank you very much. Thanks to Robin and the organisers for inviting me to come and talk today. So what I wanted to talk about is some work that we were doing over the pandemic, looking at seeing whether we could use emulation-based inference approaches to calibrate complex spatial epidemic models. And this is joint work with, particularly with Danny Williamson and Xiaoyu Zhang, and also Rob, who's in the room somewhere, and various other people. Okay. So I don't think I really need to say this to this audience, but performing statistical inference for infectious disease models is difficult. And partly that's because the models are quite complex. But actually, in my opinion, I think that the main problem is the fact that the dynamics of the models depend on things that we typically don't observe. So you can think about this as a non-ignorable, large-scale missing data problem. Okay. So when we think about statistical inference, we really need statistical inference algorithms that, in some sense, impute or infer this missing data in order to make these problems tractable. Okay? Now, there are lots of really, really nice gold standard algorithms. We've just heard two very nice talks on MCMC and particle MCMC methods. I'm a huge fan of those methods. But what I would say is that they are computationally intensive, and they are difficult to scale and generalize, particularly if we're starting to think about whether we can do these things in real time. And so I think there is some scope for looking at alternative methods that may be suitable in certain situations. And I should say that all of these challenges get exacerbated as we have more parameters, because then we have a higher parameter space to search, and as the data get more complex. So the motivating example for this work is COVID-19 in England and Wales. And this is our original model. This is not too dissimilar from many of the models that were developed during COVID. So essentially, individuals start susceptible. If they're infected, they enter a latent infection state. And then they can progress down different pathways depending on the severity of symptoms. So we sort of have an asymptomatic pathway here, at which point individuals recover, or individuals develop symptoms, and then some of those individuals will recover, some will pass away, and some will go to hospital where they will recover or pass away. Okay? And obviously we have parameters in this model that we want to estimate that govern the amount of time that's spent in each of these compartments. But also, it became very clear early on in the pandemic that there was a very strong age dependence, particularly in terms of the probability of progressing down one of these more serious pathways, right? So if you got COVID and you were older, you were very much more likely to end up with a more severe outcome. And so the model also has age-dependent probabilities of transitioning down these different pathways here. Okay? Now, on top of this, because we've got this age structure, we also have this transmission term, and the transmission term also has an age dependence, fairly classic way using contact matrices and things, and so we use the sort of the polymod data and then latterly the comix data to kind of drive transmission. But what sort of makes this model kind of more challenging is the fact that we originally developed this in a piece of software called MetaWards, and MetaWards is a general purpose simulation package that embeds epidemic models on top of mobility data, so specifically commuter data, right? So what we have is we have commuter data that governs where individuals move in different spatial regions in the country, and the movements are split into kind of systematic commuting patterns and also more random sort of non-commuting movements, okay? And so we decided to model this at what's called the lower tier local authority level. So for some context, there are about 330 LTLAs in England and Wales, just over. And essentially the model is moving individuals between those regions. So this is a big coupled metapopulation structure. Okay? Just to give you, I mean, it hasn't come out brilliantly on this screen, but just to give you some indication, this is an example simulation, this is not real data, but just to give you an idea of the sort of the resolution of the data. And so what we were trying to do was to say, okay, could we calibrate this where we're really interested in tracking trajectories in each of these regions simultaneously, right? That's what we kind of want to do. Now, I'm going to be focusing on simulation-based inference techniques. So these are techniques that, at least in theory, can work with black box models. And these have some advantages, right? Particularly in the sense that it's actually much easier to develop and update models if we're simulating from them. That's certainly a lot easier than building bespoke MCMC code, for example. And there are inference techniques that utilize these, so things like approximate Bayesian computation or particle MCMC. But the challenge here is that these typically require us to evaluate our model hundreds of thousands of times in order to fit the data. And in our case, even though this is a heavily optimized model, we're talking about the orders of hours to run a single simulation, right? So if we're going to have any chance of doing this in the future in real time, we clearly can't just use naive simulations from the model. So what we're going to try and do instead is to use emulators as a way of speeding up this process. And for those of you that are not familiar with emulators, emulators are basically fast surrogate models that we can use in place of our complex model. Now, emulation techniques have been well developed. They've been used on a wide variety of problems in a wide variety of different fields. We discovered some specific problems that we had to overcome for our COVID model. I'm going very quickly through them. One is that this is a stochastic infectious disease metapopulation model, and there are certain behaviors that one can get in outputs from the model that are kind of quite difficult to emulate with classical emulation tools. Also, the way that these models are usually used is that you would build an emulator for every data point you have, and then combine that together in some kind of way at the end. And in our case, we have a very large number of spatial regions, we have a large number of age classes, a large number of time points. So potentially we would be building thousands of emulators, and the time it takes to do that and to validate them would essentially negate the benefit we would get from using them. So this is not a problem. One thing which I think is obvious when I write it down, but it turned out to be a massive problem for us, was that if you're using these forward simulation models and you care about tracking trajectories, then how you seed the epidemic, how you introduce, particularly in the early stages, you introduce infection from external sources becomes really, really important, has massive impacts on the spatial trajectories, okay? And in theory, we could build a model for this, but it's not, or certainly in my head, I cannot think of how we would build a model for this, okay? Because it's likely that many of those early infections were quite stochastic in nature, people going on holiday, coming back, and so on and so forth. So this became a really tricky thing to deal with. So what do we do in the end? So our approach, we've got 3 steps really here. The first thing is that we introduce a model discrepancy process. So we simulate from our complex model, and then we add some structured noise to this, okay? So just to confuse people from the other talks this morning, X here corresponds to the outputs of our model, Y given X is this model discrepancy process, and then we have an observation error, so Z are our observations here, that map the simulated states to the data, okay? Now, I say this is an idealized zero mean discrepancy process, but it's not just zero mean noise, so this is structured in such a way as to make sure that when we add this noise, we are getting epidemiologically valid simulations. And this process serves 2 purposes. Firstly, to reflect the fact that we know our model is wrong, and we know that there are processes acting on the model that are not, well, processes acting on the system that are not in the model. But also, it gives us a mechanism for introducing infections in the early stages, which we don't have a model for, right? Now, we combine this with particle filtering, which Alicia has done a lovely introduction to already. And I think that this is also super important. The idea that you're going to be able to just simulate directly from the model and expect it to match trajectories in space is just not going to happen at this scale. So you need some way of conditioning the simulations on the data. But a side effect of using particle filtering is that we get likelihood estimates. And if you think about it, the likelihood is a really nice relative measure of how well your model fits the data, right? So it is a very informative, one-dimensional output that we can emulate. So rather than trying to build emulators for every data point, what we have decided to do is to use filtering, get log likelihood estimates, and then emulate the log likelihood surface and use that to drive our calibration. And the sort of side effect of this is that these ideas could be integrated into general purpose software. So then the question is, well, how do we use emulators? So this is a very simple one-dimensional toy example. Okay, so I want you to imagine that I've got a parameter here, and I've got some log likelihood, and I can take a small number of runs at different parameter values, run my complex model, get estimates of the likelihood. Okay, and then the idea is I use these runs here as training runs, and then I build an emulator. Okay, and the emulators that we're going to use are Gaussian processes, or in our case, we're going to use deep Gaussian processes. But essentially, once the emulator is trained and validated, then it's very fast to evaluate, and so we can use that to basically explore the parameter space and get predictions for what we think the complex model would give us at the points where we haven't run it. Okay, so if I do that here, then the black line here corresponds to the if you like, the point estimate or the mean for our emulator. But crucially, we know that the emulator is an approximation of our complex model, and these Gaussian processes give us an estimate of that uncertainty. All right? And when we're thinking about how to use this in calibration, we want to be really careful to include that uncertainty in our calibration to make sure we're not being too, what's what I'm trying to think of, to make sure we're being a bit more cautious. So in terms of how we use the emulator for calibration, we're going to use a technique called history matching. This is a variation on history matching because history matching was not really designed for calibrating log likelihood surfaces, so this is our kind of version of it. And what we're going to do is we're basically going to define a region that we want to be able to identify. So we would like to be able to identify essentially the area of high posterior mass. Okay, we have uniform priors here, so that corresponds to the area of high likelihood. Okay, and so what we do is we define a region whereby if the likelihood or the log likelihood is above this region, then that's something we're interested in. And if it's below the region, then it's something we're not interested in. Okay, and so here, this dashed line here corresponds to the true likelihood, so that's the thing that we haven't observed, and then we've got this sort of emulator approximation of this. And the way that history matching works is that it defines a measure, which we call the implausibility measure, and so here, because at any of these time points the emulator is a stochastic process, what we're asking ourselves is, okay, based on the emulator probability and its variance, what is the probability that the true likelihood lies within this region of interest? And if that probability is greater than some threshold, then we will retain that part of the space, okay? And so that's what we're seeing down here, right? So we've got this probability measure here, and we want to remove any parts of the input space where this probability of being within this region of interest is less than, say, 5% in this case. Okay, so if I do this and I calculate the implausibility at all of these points, you can see that even though the emulator is not really very good at this stage, it's not tracking the likelihood exactly, there are regions where even after we account for all of the uncertainty, we can still remove this part of the space. The emulator is saying, well, there's a very low chance that you're going to get a good model fit in that region. Okay. Now, obviously, we want the emulators to get better. So history matching will iterate through a series of stages where at each stage we can add more training points within this green region. So if I flick back here, so see, for example, that I've added another training point in here, and then I can refit the emulator, and then the emulator gets better. Okay? And as the emulator gets better, I can cut out more space. So here, adding a point down here in sort of this green region here has a huge impact. And now suddenly the emulator is looking much more like the log likelihood, and I'm cutting out more space. And I can continue this until I end up with points in the region of interest. Okay? And so this is the basic kind of technique. So we have this sort of iterative process. Now, with the real data, we have some further difficulties because, of course, it couldn't be, there had to be something else. One of the problems we had is that we were trying to use publicly available data, and it turns out that the publicly available data are not resolved at the same level as the model. So in particular, we have death data that is available at the LTLA level, okay? But not by age. So we have spatial data, but not by age. We have deaths by age, but only at higher aggregations. So we have two sets of death data that are correlated, and it turns out that if you aggregate them up, they don't match, which is annoying. We also have hospitalizations, but hospital cases are only available at higher level aggregations, and incidence is available by age, but not the same age categories, and again, these higher level aggregations. So we have a sort of range of different data sources available, and we had to have some kind of hierarchical latent variable approach to be able to map the model to the data. So then the question is, okay, does it work, right? So this is simulated data, okay? So what we did here was we took our model, we introduced seeds over time using this sort of random model discrepancy process, and what we ended up with was an outbreak that looked like this. Again, it hasn't come out very well on the screen, so I apologize, but this is after 54 days of our simulation. You can see that we just happen to have had a big outbreak in the northeast, okay? And then what we're trying to do is say, okay, can we recreate this by fitting our model? Using this model discrepancy process to try and figure out where we need to add infections. And so these are the predictions. So once we do 10 waves of this history matching, and then this is the ensemble mean prediction for those green regions you saw earlier in these different spatial areas. And hopefully you can see that it seems to be doing the right thing, right? In the sense that it's not perfect, but it is picking up that there is a bigger infection here. If we aggregate all the deaths across the whole country, the blue line here is the observed data, the black line is the ensemble mean. So you can again see that it's sort of doing okay nationally as well. These are the hospital cases in these different regions, and again, it seems to be doing okay. And these are the, sorry, this hasn't come out very well, but these are the age by regional level deaths and hospital incidents. And so you can see, hopefully, that it does seem to be working. And the key thing is here that this has only taken, I say only taken, but it's 2,500 runs of our model, right? Which is not a lot, I don't think, for a model of this complexity. So we've also applied it to the real data. And again, it's not done badly. It's not quite picking up this big outbreak that happens. So this is at day 54 in the real data. It's a little bit smoother than we perhaps like, and we have kind of ideas as to why this is so. If we aggregate up, we can see that it's sort of under-predicting a little bit at the beginning, and then it's coming back up again here. Part of this is driven by the fact that actually another complexity with the real data is we only have hospitalizations for a certain time. We don't have them at the beginning. So there's actually a bit less information to constrain these trajectories in the early stages here. But it's doing okay. It's not perfect, but it's doing okay. So just to summarize, this is, I think there's a lot of stuff that still needs doing in this area, but at least as a kind of idea, I think this idea of embedded model discrepancy and filtering and then using emulation does show some promise in terms of solving tricky issues with these large-scale simulation-based approaches. I'll clarify that the fastest filters that we had took about 2.5 hours to run. Some of them took 11 hours. And that's only for 50 particles and for 30 days, right? So these are very computation intensive, whatever you do. So I can't see that you would be able to embed this sort of thing within an MCMC algorithm. I think that you'd have to use emulation if you wanted to do these sorts of models. I think what is absolutely paramount is I think we could get around a lot of the problems that we have if we had better particle filters. So we're using bootstrap particle filters here. I think we need better look-ahead filters like auxiliary particle filters or the twisted particle filter. But they have their own potential problems in terms of how you build these for a system of this kind of size, actually particularly because of the data aggregations cause the problem here. If any of you are interested in emulation or reading a bit more about it, we have a package, HMER, it's an R package, that does this. It doesn't do this likelihood-based emulation, but it does kind of more traditional kind of approaches. And if anyone's interested in deep Gaussian processes, Dayu Ming has this lovely DGPSI package, which is available for R and Python. So thank you very much for listening. Thanks to Juniper and the MRC and EPSRC for funding this work, and also thanks to Jasmine, which allowed us to use all their resources to run these models. Thank you very much.
time for maybe one question? Sure.
You mentioned briefly that you have some hypotheses about why there was more spatial smoothing in the data, or in the model output than in the data. Could you talk some about that?
Yeah, so I think it's two things. Well, I think what's causing it is that there is a lag effect. So what the data that we have, if you go back to this thing here, what we're actually observing here are observations that are right at the end of this epidemiological pathway, right? I think a lot of those problems would go away if we had data in these earlier stages, which we don't have, okay? So I think that there's an induced sort of lag effect, and I think the combination of that plus the lack of hospital data means that the particle filters we're using at the moment are not able to look far enough ahead to be able to constrain the trajectories in the early stages. I think that would be solved with a look-ahead filter, but I think look-ahead filters are going to be difficult. I spent a little bit of time on this before funding ran out, but I think that's what's needed. Because that way you can constrain the trajectories at earlier time points based on information at later time points, which is the thing we currently can't do. So I think that's what's causing it.
Thanks very much, TJ.
Thank you.